Okay, then I think we'll make a start. So, welcome to this webinar, which is part of our Blue Skies Green Future series of talks from some of the eminent scientists in the field who are contributing to the sectors around the foundation industries. This is run, as you are no doubt aware, if you're here, via the Transforming Foundation Industries Network Plus, which is looking at pulling the community together around those key foundation industries across the whole UK. Just a quick reminder before we kick off. So first of all, I'm Cameron Playdale-Pierce. I'm one of the co-directors, part of the management team of the TFI Network Plus, and look after, to a degree, the metal sector. So it's appropriate, I suppose, that I'm introducing Mark to you today. You can still join the network at any time if this is not something that you haven't already done, by going to the network, tfinetworkplus.org. All benefits of the membership will you have all access to any of the publications that we're putting up internally, such as some road mapping documents and things like that have gone up recently, and also newsletters and updates of the latest things that are happening with regards to the network. Obviously, you can follow us on all of our social media networks as well. And the most important date for the diary at the moment is the upcoming TFI Network Plus manufacturing, energy efficient manufacturing workshop. That's scheduled for Wednesday, the 23rd of June at 10 a.m. And we'll be running that, looking at introducing technologies and innovation that impact energy efficiency within the foundation industry sector manufacturing area. So I believe Debbie will be dropping some registration links into the Zoom chat here. And if you've got any questions about that or wider about the Network Plus, she'll be there to address those during the talk today. So just to introduce Mark himself then, somebody I've always looked up to for a very long period of time, absolute legend in the materials and characterization area. Just in terms of his background, after getting a first-class honours degree, he went into industry and then moved back from Leeds University to Sheffield in 1989, which I Googled is coincidentally the same year that Scotland lost the under-16s World Cup final on penalties to Saudi Arabia. So that's not a statement of things to come, given that I won't mention the scoreline in case anybody doesn't want to know, but things might be going somewhat predictably on the other channel. Established some state-of-the-art facilities in electron microscopy and tribology. I know how difficult that is because I've been trying to do it myself for a number of years. And now a professor, as I think most of us know, at the Materials Science and Engineering Department at the University of Sheffield. His research focuses a lot on aberration-corrected electron microscopy. He looks at the atomic structure of materials and interfaces and surfaces, looking at the ability to understand microstructural changes that occur due to sort of frictional wear and applications in diverse areas such as artificial hips and things like that. Really interested in surface phenomena and the oxidation of metals in particular during metallurgical processing, and understanding the microstructure evolution during processing of metals for titanium, magnesium, like alloys, I suppose, and steel microstructures. And I'll just throw my own 2 pennies here. I was particularly excited by his latest paper in Nature on the effect of copper in steels, which was really exciting for all of us steel nerds who are interested in that sort of stuff. So just to introduce the talk very briefly, I think we're all aware that the key elements are in short supply. And that's probably going to induce a high level of price volatility across the sector. So from an economic standpoint, there's reasons to be able to design for sustainability from that perspective, but also the sources of these alloying elements or elements that are key to certain metallurgical families are going to become an increasingly short supply. And we need to understand how we're going to deal with that through innovative alloy design. And so amongst other things that Mark is doing, one of the major programs that he's been working on to try and influence this is the design of alloys for resource efficiency, or DARE consortium. And I think that will probably form a little bit of the basis of this talk that Mark is going to deliver now, to educate us all on how to sustainably design new alloys for the 21st century. Over to you, Mark.
Right, thank you very much for that kind introduction. I had no idea about Scotland in 1989. There we go. It's good I've learned something as well. So yeah, I'm going to talk this afternoon about a large EPSRC program that we had on designing alloys for resource efficiency. Before I go on to introduce the subject, I just need to acknowledge all the people that did the work. So I just directed, and these people were at the coalface doing the hard work. So we've heard much about sustainability, resource efficiency, and so on. It was very prominent in. My stopwatch is going completely mad on me. Shut that up. Very prominent in many statements that were made throughout government and so on. So I've just put a few up here on the screen at the moment. So the issue of sustainability has attained unprecedented prominence on both national and international agendas, occupying the mind of businesses and governments as never before. I'm not convinced we have done that, but that was nevertheless what was said a few years ago. And Julian Allwood's statement, materials influence every aspect of the energy system. Therefore, as well as developing new materials for energy generation, we must engage in public debate about limitations of future innovations and conservation of existing materials. So all very good words. And of course, it applies across a very wide range of different sectors, whether it's from aerospace, transport, energy generation, etc. It's pretty much a universal issue. So as Cameron introduced, we will run out of elements. There are many different ways of presenting this data, and some, like aluminium, we have reserves to take us forward a very long time in the future, but others certainly are much more restricted. So on this graph here is one particular set of data, and the short band in each case is how long it will last if the world is using it, and then there's also that is how long it will last if we consume it at the rate that the US is consuming, and they are consuming far quicker than many. But maybe that's more of a political statement. But nevertheless, you can see there's a wide range of different resources that we have, some running out much earlier than others. So that, just to put it in perspective, just for a few, this was done a few years ago, but if you were born in 2010, then antimony will be running out fairly soon. Interestingly, lead and indium. And so that gives you an idea about your lifespan, about how long some of these resources will last. But of course, there's not just the issue about how much resource we have. So rare earths there's a very long resource of rare earths, but of course that is affected by the location that they come from. So this graph gives you some idea about the rate at which we have increasingly used our resource. So this shows the global production of various different metals. It's normalized to 1950 being one. And so you can see that some, such as tin, haven't gone up a huge amount, but others, such as molybdenum, nickel, chromium, the usage has gone up very substantially in that time frame and continues to rise. Quite the opposite direction of what we need in terms of protecting resources. As Karen also mentioned, then the price instability is another major factor that drives our usage. There's a much publicized price rise of rare earth elements that occurred in 2011 when the Chinese chose to put on export controls, and the price went from at one point around about 30 on that scale up to a factor of 10 or more higher. And that has subsequently driven a lot of research into how we can reduce the use of rare earths. That can be done in some areas such as magnesium, which I'll talk about later. But of course, in some areas such as magnets, that's going to be really problematic. And then on the right there, you can see the rare earth oxide prices since 2016, so much more recent data. And indeed, there's quite a lot of volatility. particularly in Turbia, Lanthea going up quite substantially. So these are the challenges that we're facing. For some reason my slides have decided they don't want to. That was better. And even within looking at the price of raw materials within supply, for example, here into the steel industry, we can see the price of ferromolybdenum has gone up very significantly since 2002, where on that scale it's gone from what, 3 or so up to around 40. But it's very volatile. And again here, the price going up of various different things: manganese ore, iron ore, chromium ore, and coking coal. So that's just relevant to the steel industry. But it's a similar message across the board. Price fluctuation is a serious issue for us, and as well as our limited resource. And that's before we even get to the amount of energy that's embodied within the materials, and of course the CO2 emissions that come from producing this material. So I won't dwell on that, but it's all pretty scary stuff. So what I want to do with the talk is to go through some specific examples of where we have used this approach to try and reduce the reliance on scarce resource. And of course, one has to do these things bearing in mind that when we're going to do this for any particular industrial sector, then this usually has to be done at the same price, if not at reduced price. And so you are looking for often improved product performance at the same price or reduced price. So I'm going to start talking about steel, and we know how much, of course, in this audience, how much steel underpins UK manufacturing. There's many that don't understand how much steel influences our everyday life, whether it's construction, transport, or just engineered goods, and certainly within the energy sectors. And just some statistics, which you may well have heard of these. I could pluck out many of these, but the amount of steel in use for the world today is equal to more than 200 kilograms per person, which is huge across the whole world. And there are many statistics I could give on the importance of steel. Of course, it's had a checkered history. So this is Redcar, which I was looking around when it was up and running again, when it had been bought out, but okay, it's also shut subsequently. So we know how competitive this area is in terms of our own industry. I started my career, Cameron said that I went into industry. I started in the steel industry in Sheffield Rotherham area. And so this was one of the first continuous casters that was put in at Templeborough. Very exciting place to work in those days. Of course, now this is what it is today. It is now just a museum and a children's play area, and how things have changed over that period. So I want to start going through some examples where we have used our approach to designing new alloys, which hopefully in some way adds to this resource efficiency. So looking first at transport, we all know that the curb weight of cars has gone up substantially. We always like to show this graph. If you look at when I learned to drive, which was quite a long time ago, and the curb weight was what, typically, let's say 800 kilograms around in the late 70s, which when I came into driving, and now it's pretty much around about double that. As more gadgets have been added, you need a motor for everything, of course, don't you, to open your boot, to wind your windows up, air conditioning, etc. So the curb weight has gone up substantially. But this, of course, And this shows this in a slightly different way. We've got the car mass here, and then we've got the contributors there to the car's mass, whether it's comfort, convenience, which of course there in purple is the largest one. Safety has been important, and of course cars are very much safer than they used to be. And the base weight has remained roughly constant, which does tell us a story, because of course cars are larger than they used to be, and the base weight has stayed much the same, which therefore means lighter use of steel there. So that sort of illustrates it. So I learned to drive on a Mini that looked just like that on the right, and that's a modern day Mini, and a huge difference in size. Of course, as we move away from internal combustion towards EV and so on, then weight issues are different. Weight is not necessarily the primary driver in automotive, but nevertheless, it still becomes very important. So there's been a very big drive over the last 15 years or so or more to develop new advanced high-strength steels. This is a classic banana diagram where we plot the tensile strength of the material against its elongation. So this is just one of the measures that we could use in terms of the steel performance. But typically, as the strength goes up, then the ductility of the material goes down. It's fairly inevitable. And there's a lot of different steels within that banana that you can see. But the need to break out of that and to develop strength steels that have both high strength and adequate formability, ductility is crucial. So I'm going to describe one project out of two where we were involved. This is on nanoprecipitation steels, and this was done with Tata Steel. And the demand here was to have a high strength steel that could be made on existing plant and that could be made in a resource efficient manner. In other words, the cost implications were very clear. It must fit within existing cost. And the drive here was to, as you can see here, it's for the application load control arm and thereabouts in the front chassis. We don't have just this tensile ductility, which is often quoted. We need to have something that has good hole expansion, the stretch flanging. It must have good bending and must be good in fatigue. And we have to do all of those things together and produce the steel. So the adoption in the strategy here was to go for a single phase ferrite, in other words, the structure that would give the maximum ductility. So this is another version of the hole expansion of the banana diagram, where we're plotting hole expansion ratio against the tensile elongation. And most materials, again, sit in a banana shape, whether the dual phase steels, HSLA steels, and so on. So the approach was to go to a ferritic baseline and use the strategies of a fine grain size and a high loading of precipitation to achieve that, to achieve the strengths of up to 1 gigapascal that we were seeking. As I say, to develop this, there's lots of good academics that sit in their laboratories developing new materials, but then can't be scaled up and can't be used in plant or need major new investment in plant. The remit here was very much to be able to manufacture within the existing plant. So that involved rolling, finish of rolling was about 900, and then a rapid cool to the coiling temperature where it would be held somewhere in the range of 600 to 650 degrees centigrade, at which we'd get transformation into the ferrite. But the key was to achieve this interface precipitation. So that's the image on the right, which is just showing the ferritic structure of tensionism electron micrograph, and you can just about make out these very fine precipitates that are there. If we look in more detail, we can see these beautiful rows of precipitates that there's just 3 examples altogether there. And they are typically of the region of 3 to 10 nanometers in size. Now, this is nothing new. Interface precipitation was studied extensively in the 80s. It was a very popular subject then, but it never really made its way through to a commercial product. So what we did with this is to play around with the compositions, add a bit of magic dust, and to end up with an alloy that was really quite lean. The composition, the cost therefore was low, and we could produce this, as I say, very high number density of very fine precipitates within the structure. But as I say, I'm taking a diagram here that's been around for a long time in terms of the mechanism of the austenite ferrite transformation producing precipitation in the process, which of course is still a matter of debate, but it's been known for a long time. But we have the ability these days to really see the atomic structure. So in the middle here, you can see the size of the precipitates, the slightly darker region in that high resolution image, but just a few atomic planes across. And then on the right-hand side, we have the atom probe here, and showing lines of precipitates, in this case, vanadium carbides with a tiny bit of molybdenum, which is a crucial addition in there, which refines the structure and gives us this really high number density. And when we put that together and generate a very fine grain size as well, then you can see the contributions to strength that we get out of the different contributing factors. So at the bottom right there, you have the black, which is the basic strength of pure iron. Solid solution strengthening is small, but it's important. Dislocation strengthening is almost non-existent. And then the two main contributors here are grain size. And you can see this massive contribution to strength from precipitation, which is 500 megapascals or so, which is an absolutely massive amount, particularly for a steel. Of course, and I'm not going to talk about this, although I'd love to do so, that pushes into the realm of hydrogen embrittlement. Typically, when we get above about a gigapascal strength or thereabouts, depending on the specific steel composition, then we're into the regime where hydrogen embrittlement becomes an issue. So we have an image there on a failure from hydrogen embrittlement, the typical sort of intergranular failure in the middle there in the SEM image from where you get cracking extensively. Now, the good thing about the steel that we developed is that vanadium carbides, particularly the very fine coherent ones, are very good at trapping the hydrogen. So if you do get hydrogen ingress into the material, then particularly the semi-coherent, slightly larger precipitates, then they're very efficient at trapping hydrogen. And so the deficit in strength from hydrogen embrittlement is far, far less than it is with some of the competitor materials such as dual phase steels and so on, where the deficit can be much larger. Okay, so that was the first example. The second example is looking at copper in steel. And there are obviously ongoing projects about reducing the level of copper in steels. Copper is very detrimental, for example, in terms of hot shortness. So you have an image here of where you have hot shortness cracking. And I won't go through the mechanisms of this, but it's clearly associated with copper. And we know that copper comes into recycling, and there is, as I say, a major drive to reduce the copper content in recycled steel. But we had some thoughts about this and thought about, well, okay, can we be more tolerant of copper in steel? Is there a way of developing steels that are? And so we looked at this, and of course there is steel grades that are used which have higher copper already. So there's A707, which is a forging steel used for example, tension legs and oil platforms, which is very high strength copper bearing steel. And then another example, several, is 17.4 precipitating hardened stainless steel grades, which again, there's 3 or 4% copper in there. But these are really very specialized steels and not for wider. So as I say, we had a project to try and think laterally about whether we could develop a steel that could be made relatively straightforwardly, that could deliver on our challenges of having high strength, be made on existing plant, be processable, and within at least the same cost, or if not reduced cost. And I don't have time to go through the rather interesting story and the way we went, but we started taking a baseline of an iron manganese steel, and we started putting in copper in amounts of 1, 2, and 3%, up to 4%, in fact, expecting the thing would just fall apart and it would all be a nightmare. But in fact, we found some very interesting properties. And we found that if you cold roll the steel, so it just needs a conventional hot rolling process, and then you take it through and give it a cold roll, and then flash anneal it, so a very short anneal, you can get recrystallization to a very fine grain size. So that's quantified on the top left there. So this is in microns. Those of you familiar with steels know that commercially it is really difficult to generate grain sizes that are less than 2 microns, say certainly less than 1 micron becomes really challenging. But here we had a steel where we had a very large proportion of grains that were down at that very fine range. So you can see the EBSD image, you could have seen if that didn't disappear, in the middle there. And you can see the grain size distribution there with a scale bar of 10 microns. Now, during that flash anneal, what we do is to precipitate a very high number density again of copper precipitates. So the bottom left there shows the distribution of the very fine copper precipitate, showing up as bright blobs there. And in the middle bottom, that's an atomic image showing the interface between the iron matrix, which is FCC in this case, which still does have some copper in it, but it's predominantly iron manganese. And then these regions that are precipitates, which are copper rich, but they also have iron in them. We have perfect coherency between them. And as you can see, they really are very fine in the sort of 2-3 nanometer range. Just to quantify that a bit more, there is the atom probe data from this material. On the left, you can see the atom probe tip, and you get an idea of the very high number density of copper precipitates there within the structure, as I say, that are perfectly coherent. And one thing we found is that this microstructure is really very stable to high temperature. So we're plotting there the 3 different alloys. The black is for 0% copper, so the baseline material. The green is 3% and the blue is 4% copper. And you can see the baseline material when you get to, if you start off and get this 2 micron grain size, as you heat it up, it very rapidly grows and you get very rapid growth even within this time frame. Whereas the 4% copper is really quite stable. The 1 micron grain size, which of course has got a very strong driving force for grain growth, nevertheless stays stable even with an hour annealing up at high temperature of 900 or thereabouts. So looking at the mechanical properties, we've really achieved something that was quite interesting as well as impressive, I think. The yield strength with 4% copper alloy, typically about 700 megapascals, which is pretty respectable. It's not outstanding. But of course, the difficulty is getting both a high yield strength and good work hardening behavior so that you get a stable and large ductility. So you can see from the curve there, sustained linear work hardening up to a true strain of about 0.45. So we get this massive ductility, taking the material strength up to just shy of 2 gigapascals. And one might say, well, how do you manage to get such high ductility in an alloy that's basically precipitation hardened? Because if you look at all precipitation hardened steels, indeed like the previous example I gave, then you do not get this high ductility. And so what we believe is that the copper precipitates are not actually giving you strengthening per se. You just get shearing of dislocations. They seem to be able to go through the precipitates really uninhibited. But what the copper is doing is stabilizing that very fine grain size of 1 micron or thereabouts. And then the deformation mechanisms are in fact through a twinning mechanism, which is quite different. But you can see top right there, those are all the steels, all the wide range of high strength steels plotted. So on the vertical axis, we've got the product of the strength and elongation, and on the bottom axis, there we've got the yield strength. And generally, you can see that this relatively straightforward iron, manganese, copper steel achieves far superior properties to the others. Just to show you some beautiful images, this is the TWIP, or the twinning induced plasticity that is taking place during deformation. You can see these beautiful twins. And when you go to high resolution imaging, you can indeed see that there is some transformation to hexagonal phase there as well. So we get both a trip and a TWIP effect, and that is what is responsible for getting this very high ductility. Okay, so that's steels. Now for something completely different, I just move on to magnesium alloys relatively briefly. So magnesium is around quite extensively as cast alloys, but wrought magnesium alloys are far less used. One reason is they tend to be quite expensive. A second reason is also that they do rely on rare earth elements because otherwise we will not get adequate formability. And I'll just skip that, I think. So again, it's something that's not new. We seem to be reinventing science that we've done before. So magnesium has been around quite a while, if you could afford to put it in. So there's a Jaguar Mark 7 that have very extensive use of magnesium in it for lightweighting. Indeed, Porsche use it, and there's a future predicted car from Volkswagen. But the Achilles heel really is the cost, which comes back to this reliance on rare earth elements in order to allow sufficient formability in the alloy. So so the wrought alloys tend to be these rare earths, so typically magnesium, yttrium, gadolinium as an example. And it all comes down to the crystallographic texture. So if you have a standard magnesium alloy, then it has a very strong texture, crystallographic texture, where the basal planes become all aligned, and you can see that in the bottom series of there, where it shows you a very strong texture of the basal pointing vertically upwards. And the consequence of that is when you form these alloys, you can see what you can get in the right-hand image, where you get extensive cracking. So we've known for a long time that we put rare earth elements in, we distribute this texture, it becomes much weaker, and as I say, the crystallographic texture is distributed over a much wider range. Now, I won't go into this in detail, although again, I wish I could, but understanding that texture and why it evolves in magnesium alloys is something that is of interest. It's also quite controversial. These EBSD images show where some deformation has been put in, and we get extensive twinning in the structure. And there are different types of twins in there. We have compression twins, tension twins, and so on. So I say I won't go into the detail. But these play a very major role in developing this crystallographic texture. And I had this wonderful postdoc, Takehome, who would happily sit there and take the same part of the microstructure, deform it, prepare a region, then characterize it, then he would deform it again and or recrystallize it again, depending on what he was doing, find exactly the same area and follow this process through. So you've got 4 images there showing a progression, in this case, of recrystallization. On the top left, you've got the twins, and you can start to see, in this particular case for tension twins, recrystallization comes along and it consumes all the structure. So you can see it growing from the right-hand side, comes across to the left, and in the bottom left image, then it's consumed the whole structure. And that gives you the very strong basal texture that we're familiar with. On the other hand, in double twin variants, it's quite different. Then recrystallization occurs within the twins. And as these grow, they tend to give this distributed texture, which is what we want. In other words, not a strong texture. So the question here is, are there other additions that we can put in that would do the same as the rare earth additions? Now, there's been a lot of interest, and COSCO have led on this in producing magnesium, calcium, zinc alloys, where calcium seems to behave very much in the way that the rare earth elements do. So to cut a long story short, this is quite a lean alloy, so magnesium with a small amount of calcium, small amount of zinc in. We now get a very uniform grain size within the material. And as you can see on the right-hand side, then the texture is nicely distributed, and it's a very weak texture. So we know that this alloy is very formable, and we know it also has adequate corrosion resistance, which is really going to be important, although protection is well advanced for these alloys. So manufacturers such as Volkswagen have been looking at these magnesium alloys as possible commercial viable routes. And the trick here is with this is the calcium. It's a large atom relative to the magnesium. It segregates the boundaries, but it does play pretty much exactly the same role as the rare earth elements do in terms of forming that crystallographic texture. Last but not least, I'm going to go through this relatively quickly, but I just wanted to mention titanium alloys as well. Where there is a lot of interest in the beta titanium alloys for applications such as undercarriages, where really to strength, but they also have much lower stiffness, and so there's much interest in biomedical applications. Now, much of these alloys have been developed on the basis of what's called bond orbital, d orbital energy level graphs. So we plot these 2 variables, and that's just a plot there of all the different alloy additions that have been made. And you can get yourself another paper by putting yet another alloy composition within there. But again, it's a very similar story this to the steel. The parallels are very similar in terms of developing an alloy that can offer you both high yield strength, high work hardening, so that we get the good mechanical properties, but equally that has additions that are quite straightforward, like iron, chromium, and so on. So this is one alloy where we have achieved that. We've got a yield strength of 700 megapascals, which is high for a beta titanium alloy, and also nice uniform work hardening that takes us to a true strain of 0.4, which again is very substantial. And as I say, the parallels with the steel is very similar. We're using this transformation-induced plasticity and the twinning-induced plasticity beg your pardon, and transformation-induced plasticity together. So if we get both of those mechanisms taking place, then we can generate these very high strengths. And I just can't resist showing some nice images of those two mechanisms taking place. And you get these very beautiful microstructures. So I think the take-home message there is there's some interesting parallels between different metal systems where we can use the same basic mechanisms to strengthen the alloy. Okay, I think my time is up of what I was allocated. So I think there's take-home messages. There is a lot of scope really for still designing new metal alloys, but doing that in a resource-efficient way, looking at that as a key determinant of design. And we can still do that to produce something with high performance and with no cost implication. Okay, that's it. I think I've come to the end. So I guess I should stop sharing that screen.
Thanks very much, Mark. And some virtual applause, I'm sure.
Yeah, I can hear it ringing in my ears.
Yeah, really a really interesting and thought-provoking talk. We've had one question come in on the chat, which we'll start with, and then as you might expect, I've got plenty of my own as well to keep you busy if necessary. So the first question came in from Shahid, and I wonder whether Shahid, you wanted to unmute and ask the question yourself. Otherwise, I'm more than happy just to read it out.
Thank you, Cameron. Can you hear me?
Yes. Yeah.
Just about. Yeah.
Well, thank you very much, Mark. It was very, very interesting related to the alloy development. This is I always fancied this area. I mean, looking at one is now is absolutely wonderful. My question about this copper thing, which you said, because my background from the steel industry, so I'm more interested to look at. I mean, it's just like have you? I understand your experiments were the lab scale. You try to add sort of like copper in that one, and try to see what the copper is doing with the grain size and with the precipitation and the strength and ductility. I mean, have we done anything like taking the scrap, I mean, as a raw material and adding into a bit of in the steel and try to see how the copper is transforming from scrap to the steel? And that will be a true reflection that how the industries basically will be coping with the issue with the contaminants in the scrap coming. And the second, the relevant is the copper, the precipitate. You said that one is like a single copper, like a virgin precipitate. It's a composition. It's a composite of some sort of like a precipitate, which is a copper as a more dominant controlling factor for the grain sizes.
Right. Okay. Yeah. In answer to your first question,
it makes sense.
Sorry. Obviously, the route through from scrap is important. We haven't done that because we're laboratory scale melting, and so that would be rather, and we needed to control the experiments to really understand the mechanism. But clearly that would be a follow-on. But nevertheless, I mean, we're putting 4% copper in, so you'd need to make copper additions intentionally. In answer to your second question, I mean, we call them precipitates, but they are regions of higher copper. Structurally, they're almost identical to the iron matrix. Lattice parameters are very, very similar. Structure is the same. So that interface between them is not really a barrier to dislocation glide, but the size and number density is enough to give you Zener pinning of the boundaries, and it seems really quite effective as a Zener pinning. So that's the primary reason that we get this very fine grain size and can retain it. And the key is to get the copper to precipitate at the same time as recrystallization. So you cold roll it and you drive the recrystallization, but at the same time the copper is precipitating. So it's pinning the boundaries as they form. So you could call it just pure good luck, actually, that the two occurred at the same time. It'd be nice to claim it was a great scientific breakthrough in that way, but I think as much as anything, that was just pure luck.
Thank you, Mark. It was really nice, very nice. Thank you very much indeed.
Thanks, Shahid. Mark, I think there's quite a lot of amazing scientific discoveries that involve good luck. So
yeah, well, this was all the way through, really. And I thought it would be a waste of time and that we'd, end up in disaster. But it was a happy story, which is nice.
Yeah, well done. The next question I think is coming in from Animesh. And just before Animesh, you do ask your question, just a reminder to anybody else who wants to ask one, please do drop it in the chat and I'll try to squeeze in as many as possible. So Animesh, over to you, I think.
Hi, Mark. Very nice piece of work. Congratulations. You might recall Professor Bob Cochran at Leeds.
Yeah.
He, myself, and Rick were involved in recycling of scrap steel, funded by EPSRC, and we demonstrated wire drawing from this scrap steel, which had both copper and tin.
No,
But the clever trick we played was mixing with aluminium. Okay, I think we published the paper. We wanted to take it forward, but British Steel at that time was in great difficulties, beginning of this millennium. My question to you is what the gentleman before asked. If you have tin and other deleterious elements, which is very likely, would you envisage a process where you might want to do processing of liquid alloy by refining and then reprocessing as you propose? That's my question one. And second question is on vanadium containing. So I'll come to that later on.
Okay, I mean, yeah, I mean, you're not the first to ask that question in relation to tin and so on. So I can't really answer it because we haven't done it. But that is the obvious next step, and that's one thing that we are interested in looking at. So you're obviously further ahead with the wire drawing. I mean, it's interesting you had aluminium in there, which of course is, you know, for many steel makers is not the favorite addition that they have.
We didn't add much aluminium. There wasn't much aluminium, but it definitely helped us to circumvent all the hot shortness related problem and maintain very good drawability. My second question is about the vanadium. You mentioned that hydrogen embrittlement is reduced by vanadium carbide. First part of that question is, how did you measure hydrogen if you have vanadium carbide? And second part, if you were able to measure, were these vanadium carbides not fully stoichiometric, i.e., because carbides have very large, particularly vanadium carbide has large non-stoichiometry.
Okay, so in answer to your first question with the hydrogen, there's various ways of looking at it. You do hydrogen permeation studies, you can do thermal desorption studies and then if you do some assumptions about the activation energies of the various traps, you can separate out the contributions from dislocations, grain boundaries, and the precipitates. And indeed, you can separate out the finer coherent precipitates from the coarser semi-coherent. The second part of your question, you're absolutely right that the defect structures are really important. And I'd love to talk about this in detail, but probably isn't time. But I think if you look at titanium carbide and compare it to vanadium carbide, they've got very similar structures, but in fact, the vanadium carbide defect structure is different. And that allows hydrogen to actually go in the particle, which is controversial, except whereas normally it would sit at the interface. So we did deuterium charging in Atom Probe and showed the deuterium went into the carbide with the vanadium variant, whereas most people have shown it's at the interface. So yeah,
thank you.
Really interesting topic. Very interesting.
Thank you for that, Animesh. A really interesting discussion that's got us all thinking. Next one, Mark, is a wider question, which I was interested in as well, actually, around HEAs. I don't know, Max, whether you want to unmute and ask your question.
Yeah, sure. So just a question from a sustainability perspective, really. Thinking about the massive trend towards increased complexity in alloys, and also having a different alloy for every different application. What the sustainability of that is. Do you see that there is a place for complex concentrated alloys, for example, in like mopping up lots of elements that end up included from recycling and such, or do you just see it as nothing but trouble?
Yeah, I think it's very interesting. A lot of people have suggested that high entropy alloys, because of the mixture of different elements, is right area to look at for resource efficient approach because of the ability to recycle. And so I think, yes, there's much scope there. Of course, quite a few high entropy alloys don't have all the right elements in, cobalt based ones, which cobalt is massively expensive and getting worse. And it's not as, and we're using more and more for all sorts of other applications. So I think you have to take each one on its own merits, rather than talking about them, HEA as a whole, because there are so many different ones out there. But I think there is real scope there, yeah, absolutely.
Thanks for that question, Max. It was really well put. Nothing but trouble is an interesting way of putting the question. I don't see any more questions in the chat. I'm going to ask one quickly myself, just because I'm burning to ask this question, and then we'll probably have time to fit one more in, I think, if anybody thinks of anything that they haven't asked already before the end of the session. So Mark, it's similar thread really to what Max was talking about, but in the context of steels. When I was looking at the work that you'd done on I suppose the leaner compositions, but with using the precipitation effects, so for the nanoprecipitated vanadium carbide grades of steel, what do you think about those in terms of their sustainability impact? Obviously, they have a really important impact in terms of their combination of formability and strength in terms of down gauging in the use phase of those materials. But what about that in terms of their impact on recyclability, and how you would compare those to, say, TWIP or TRIP type chemistries, and whether they, it seems like a more sensible route to take to look at these leaner, more highly precipitated alloys?
Well, there's not much in there. The amount of vanadium is, what, if I remember rightly, 0.12. Otherwise, we're talking manganese. Yes, we've been working on trying to get rid of the moly out of that because it's expensive. But it does seem to have a very strong effect. But obviously, I would have thought for recyclability, these would be ideal because they're really lean. They're basically just ferrite with a bit of magic dust in the best way. And you can play further games as we have, is if you then basically do the same thing, but you end up with a DP type microstructure still with the interface precipitation. You can get even higher strengths out of them with still the good formability. So there's a lot of interest. But yeah, that surely is, I can't see what better you can do personally, in terms of going down the lean route. It's pretty much as good as it gets.
Yeah.
I don't know if that answers your question, but
yeah, I think it does. And then there was a second part to which I'm going to throw in just because I've got the time, which was if we then think about the reuse element of the materials, especially where you're talking about the TWIP effects.
Yeah. So
in terms of potential remanufacture of these materials, do you see the TWIP effects as an advantage or disadvantage? Because you mentioned in the context of the copper alloys that there is there's an advantage there in terms of stable deformation above yield. But then the alloy gets increasingly strong. So will we see that as an advantage or a disadvantage in terms of potentially reprocessing the material for another application rather than recycling it?
Yeah, gosh, that's a good question. I haven't thought of that. I presume it's an advantage. I mean, it's like all things. If you're developing something that has stable, extensive work hardening, then you've got a lot to play with between yield and UTS. The problematic materials are where it's very small. So, if go over yield, you've got real problems. But I would have thought that if something had gone wrong with it, then you've still got plenty of scope for I guess reforming, in terms of reusing. But yeah, I'd have to give that more thought. I'm just that's a really good question. Yeah,
maybe that'll be your next great innovation, Mark.
I wish.
I'm sure we all look forward to it. I mean, I think that on that bombshell, that really brings us to the end of today's webinar. I'd just like to thank Mark again for the contribution today and the really interesting talk that he's put together, and thank you, the audience, as well, for your questions, which promoted some really interesting and useful debate. In terms of this series, the next webinar is going to be on the 24th of September. That's at 11 AM, and that's from Prof. Lenny Coe, also from Sheffield University. Going to be a really interesting talk, I imagine, on the impact of TEAs and LCA, I imagine, on the circular economy. So I think that would be a really interesting talk that you catch up with after the summer break. And just to remind you all again, a date for your diary, the 25th of June at 10 AM is our next workshop for the TFI Network Plus, focusing at energy efficient manufacturing. So thank you for everybody for attending, and see you next time.